Okay. Yeah, let's go ahead and get started then. Welcome everybody to Community Research Call number 5. We're glad you're able to join us for this. These are our quarterly research showcases where we talk about the projects that Manifold is currently working on, what the team has been up to, as well as future directions that we're going to explore and new ways to get involved in the research and other org-wide updates. So it's an exciting sort of quarterly main update for us, and we're happy to bring this to you. This one is our midsummer one, and so it's particularly special because the summer is always a time where we put our heads down and we really push forward on all of the projects in particular. So we have some exciting updates for you guys this time. So thanks for joining us. My name is Sid Sika. I'm the head of operations, and I'm one of the co-founders of the group. And shortly, you'll hear from our founder Hirsch on what the org is, what we're trying to do here. Okay, so without further ado, Hirsch, would you take it away, please?
So Manifold is basically a new kind of research lab that we've been building for the past couple of years, and it's grown a bunch, which is why many of you are here today. We try to combine the most successful characteristics of both open source communities and academic groups, as well as very mission-driven industry research groups, to basically try and solve the scientific and technical challenges that sit in the gap um, where they are too resource intensive or too complex for academia to pursue effectively, but perhaps too far on the science validation side for industry to meaningfully put resources behind. And there's a ton of interesting problems that sit there that often nucleate, right, the most interesting solutions that advance mankind on various frontiers. And so we work in a really interesting way where we have these sort of very mission-driven groups, but we also have a large-scale open source coordination process, and we work with a lot of incredible contributors and collaborators. And I just want to talk a bit about that today and who some of those collaborators are. So at a high level, our research approach is basically can be broken down in sort of 5 stages. So we have a very large top of funnel exploration approach where we work with lots and lots of different people. So you'll be hearing about a ton of exploratory projects today. We also are actively trying to support anyone in the community starting a project and seeing if Manifold can support that. We'll talk about that towards the end of the talk today. And we sort of gate these experiments and these burgeoning research directions through different validation stages where they become more mature and ultimately turn into research programs, which often comprise clear sort of objective threshold events or large scale deliverables that we think and are sort of self-evident that actually prove some fundamental scientific advancement. So you'll hear about a couple of those programs today. Programs are intense. They take, anywhere from hundreds of thousands to millions of dollars of funding because we are effectively trying to prove something new. And notably, everything we do is open science and open source. So we do everything in the open, and all these programs are open collaborations between industry groups, academic research groups from some pretty incredible places. So we kind of think of this as a not just a research lab, but almost a research network, similar in some ways to what groups like Speculative Technologies or Protocol Labs think about. So there's a lot of these interesting new takes on how to do science in a very network-driven way, but we are extremely driven on specific objectives. So rather than take a very large distributed graph of progress, we try to make a lot of progress on very specific directions with lots of open source and academic collaborators. And we also don't view that impact stops after you get out a scientific artifact or a paper. We really want to see if some technology we build can be spun out, whether it's a nonprofit initiative or a for-profit commercial entity, to be able to bring that impact to as many people as possible. And we try to support that as much as possible and basically have built everything around that. And so we kind of have sort of 3 distinct categories of team. We have our large sort of research community, which we operate through Discord. We work with a ton of these academic groups as well. We have the OS core team, most of who you'll be hearing about today, on various projects and directions. And then we also have and are building towards full-time research program leads. So these are experienced PIs who sort of drive each of these research programs through their multi-year sort of stages of progress. Yeah, just briefly wanted to cover. So like the people that we work with are really incredible. And we are trying to build a new form of structured collaboration we call the Advanced Network. And we already have some pretty incredible teams from places like Bloomberg, Meta, Purdue, Georgia Tech, where we have strong roots, MIT, and Tufts, who are working with us on various projects that you'll hear from today, and we'll call out those connections each time. But we really think that the leverage doesn't stop there. We're trying to work with as many startups as possible. We've already had one spin out and hope to have a couple more. And basically want to drive as much impact that we can from the research that we do. And so we are basically building this collaborative network to make that happen. If you'd like to work with us on these projects at an organization level, please reach out. And I think without further ado, we can just get into program updates now because that's the real exciting stuff. So we're going to jump into research demos and updates. So I'll start by talking about Gollum. So Gollum is a very large scale program we're pursuing here at Manifold. It's in collaboration with our first spin out MedArc AI, where I also work and a couple of our team members work, as well as the Multisensory Intelligence Group at MIT, and a couple of other pretty incredible institutions, including at Tufts. And you'll hear about a bunch of different um, projects today. So the Gollum program is a very large scale program, almost comprised of multiple efforts, trying to build advanced algorithms in the intersection of joint multimodal intelligence, continual learning, meta learning, ultimately to underlie how we think about the next generation of intelligence systems. And we kind of parameterize that by thinking about them as building digital minds or engineered minds. And so you're going to hear about a huge variety of projects across multimodality, metacognition, and other related topics that underlie this program. And I think we can just go ahead and jump into it. So first we have VLM calibration, where Arithra will be presenting. Arithra is the project lead for this. Arithra, over to you.
Hey everyone, thanks for introducing. And so VLM calibration is a project that we've been working on for a while. And initially we've been working on the LLM side of things, and we would like to like move on to VLM very soon as the LLM project is wrapping up. But we have some interesting updates for that. So the motivation of calibration is to basically kind of understand whether the LLMs are trustable or not, whether they are reliable or not, because like there are often times where we can just accept whatever they say for like, and that's like not the best way to go about things, as we keep trusting these things more, and these things are more integrated in our day-to-day lives. And from LLMs, these problems kind of compound when we move on to VLMs or like more agentic approaches, where they are doing more and more of the work, and we just trust them to do all of the work right in the right way, but we don't really know what their motivation is, or like what their accuracy is at each step. They might be right, but they might be thinking that they're wrong, and that might like affect the next step. So we have a very broad set of experiments for figuring out like what to do with regard to this, and like how to verify this. We kind of try to ask them whether, uh, like looking at them, whether they have like a confidence score that they can give, or we can try to look at the logits, which kind of can try to figure out, we can try to figure out like how probable they are in their outcome, like they're outputting some option, how probable it is. And we conduct experiments across like various model families and various model scales to figure out what is the thing that's actually driving this. Can this be a problem that can be just fixed by scale? Is reinforcement learning causing some problems with respect to the base model, in the sense of like making things more overconfident? Because we train these models through RLHF, but we all humans kind of prefer models to kind of accept whatever they're saying. So in a sycophantic kind of approach, that's kind of some factor that might drive this overconfidence. So we have an interesting set of results. Sid, if you move on to the next slide. Yeah. So a lot of the times in literature, as well as like while working in real world applications, we tend to ask LLMs for confidence values, like, okay, like classify this, and what's your confidence of classification in 0 to 1 scale? And that turns out to be very useless in current models. There's literature explaining that this was something that was viable during Claude 2 and GPT 3.5, but right now with current models, Llama 3.1, Quen, Gemma, these seem kind of useless. Scale matters, but like every model kind of has their own different kind of approach. Every model family has their different kind of scaling with respect to scale. So for example, some model might be very overconfident on GSM 8K as they move like upwards in scale, whereas some models might be like very less confident in real world knowledge, like simple QA. And this we've observed like different behaviors in calibration over Llama, Quen, and like even over different data sets. We have a very comprehensive set of results that we are willing to kind of compile and publish very soon, I think. And yeah, every model kind of has their own different response with respect to chain of thought. So asking them to think about whether their response is right or not. Every model at various scales has different kinds of responses. Some tend to back off, some tend to double down. And uh, like we have designed like various scenarios that kind of enhance these effects more. Model family keeps mattering. Like, for example, we saw the previous slides where where Llama was moderately well calibrated, not very well, but Gemma as always, and Quen, like we've talked about in our previous research updates, keep remaining very overconfident in most cases, like in MedMCQA, which is probably not the best thing considering the fact that these are medical data sets or medical question and answers. Another thing that we've found is like given the model's own text, but saying that they're from another AI, the model's still confident enough. But asking the same question when given another model's answer, the model is very pessimistic. And this confirms the fact that we've seen in some other research papers going in like similar directions that models can kind of recognize their own text, but given the same answer from a different model, they're not very confident. And chain of thought often shows doubling down on their own text, but is very pessimistic on the other models' thoughts or ideas. To kind of dive deeper into these experiments, we use Olmo, which is we have their training data, which is very publicly available, and we also have this way of n-gram matching over their whole data set, the pre-training and the post-training data set. So we kind of try to figure out how concepts or frequency of concepts in the data set might be related to some of these calibration tasks or like metacognition tasks. The thought would be that like if something is much more represented in the data set, the model might tend to be more overconfident on it if something is like overrepresented in some set. Initial experiments don't really show that, but they're still very brittle, and we're still working on refining some of these experiments. And yeah, so to make these experiments more like robust, we're thinking of using NER experiments instead of n-gram matching, and try to semantic search over the large corpus of datasets to figure out if those are some ways that would reveal, okay, these models might be overcalibrated because of concept matching instead of n-gram matching. And we slowly plan to scale towards VLMs as we expand the team. We've recently expanded the team a bit, and I think that's going to help with bandwidth and things like that. And yeah, I think that's mostly it. If anyone has questions, be like sure to let me know. Thanks.
Hey, thanks everyone for taking the time out and joining. I'm actually tuning in from Vancouver, where I just presented Multinet yesterday at ICML. It was really nice to see a lot of people stoked about what we're working on, and so I'm excited to share more with all of you. I have spoken about Multinet in the past CRCs, and there's a lot of talks we've given, but I'm sure there are new folks here who haven't heard a lot about Multinet. So I'll give a brief overview and then jump into the details. So I've been leading Multinet for around a year now, and I work with some really talented researchers, some of whom you'll hear from later today. So Locke, Deb, Harsh, and we have two new, also very talented researchers, Sean and Riddle, joining the team. And so yeah, excited to scale up the project and take Multinet to the moon. But yeah, so just a brief overview of like what Multinet is and why we do it. So Multinet is kind of inspired by our thesis that today's generation of AI systems are really good at multimodal understanding, but we think that the next phase of AI systems become systems that actually take actions and become really useful. And for that, they have to have a native understanding of what an action is, and it isn't limited to just function calling, which is the limit of like AI tool use today. And a key direction for that is having good benchmarks that measure the multimodal understanding ability as well as the action taking capability of these models and systems. And all the benchmarks that are currently there in today's AI community, they're pretty specific and they evaluate certain things. And we want to have one-stop shop where we can evaluate a model or system on both its understanding capability, its action taking capability, and what makes it a really good generalist foundation model. And so the goal with Multinet is to build, probably the largest open source vision language and control eval dataset that we can benchmark these models on, have clearly well-defined metrics that kind of capture how well these models do on all these different tasks, domains, environments. And also, obviously, the biggest goal is to enable everyone in the community to use this. So an easy to use like software toolkit, which we already do have to kind of access and standardize the data. Standardization becomes important, especially in control when you have data sets from a variety of different sources, all these different formats, some that haven't even been maintained for years now. So I think that's a key contribution, makes it easier for everyone to use the data. And then obviously you want this to be a very challenging benchmark to assess how good these generalist foundation models are today. There are like vision language models today that everyone knows about, and there's a new emerging class that's like rapidly growing vision language action models, which are basically VLMs that are fine-tuned or pre-trained. Sometimes it's like architectural modifications to work on robotics datasets. And then, so that's kind of the goal with Multinet. We already do have a version of this. We have a lot of work that we've done that's already open source. I'm sure we'll share the slides with you soon, so you can check out the website and our dataset spec paper. Yeah, so the two major releases we've had so far, we called it like V0.1, V0.2. With V0.1, basically our goal was, take these state-of-the-art VLAs and VLMs and kind of like evaluate them on how they do on real-world robotics data. Now for VLAs, this is a slight distribution shift in their training data. But for VLMs, of course, it's a massive jump. They're not really trained on offline trajectories of real-world robotics. And so we want to see how well do they do, how well do models that are good at multimodal understanding adapt to action taking, and how well do models that are good at action taking, how well do they do on like a slightly different distribution of data. So we kind of curated this list of data sets from the OpenX embodiment collection, which is like this large effort that consolidates real-world robotics data across different, embodiments, tasks, environments from a variety of universities. And a few of these, as you can see, are within training for a model like OpenVLA. And this is important because you get to see how well these models do on the data that they've been trained on, and on data sets that are unseen but are very similar to the data that they've been trained on. So one thing that we notice is that overall performance is really bad. Like all of these models do not generalize well, even if the data distribution shift is minor or major in the case of VLMs. And one interesting thing is that on unseen data, VLAs have very inconsistent performance. So the performance is highly dependent on what kind of embodiments, what kind of tasks, what kind of environments. And for VLMs, we developed this framework called Genesis, which basically allows you to adapt these vision language models to a completely different domain, which is action taking, which Dip and one of our alumni, Kyle, worked on as well. So V0.2, what we did was we shifted the data distribution even further, and we said, okay, let's take the state-of-the-art VLMs and VLAs and evaluate them on 2D procedurally generated gameplay data. Now, gameplay data is very rich in action. You have visual observation and you have a final goal, and you take intermediate actions to like reach this goal. And in the case of, for V0.2, the data set we picked was ProcGen. ProcGen was an environment that OpenAI created, part of their GIM ecosystem, but we are evaluating it on offline trajectories of expert, agents that are experts in ProcGen, similar to offline trajectories that we did in robotics. So we found a lot of interesting results with this. This is just a snapshot of what the ProcGen data looks like. I'm sure a lot of you have played some of these games at some point in your life as well. So the action space for all of these games are discrete, and they correspond to like button presses or no operations. And so it's a discrete action space and mutually exclusive action classes. You can only hit one button to take one action at a given time step. Next slide, please. Yeah, so because this is a discrete action space, we had to get a little more innovative with the evaluation metrics compared to just using a mean squared error in V0.1. And so we use a Breyer mean absolute error, which basically assesses how confident these models are at predicting the right action class in the discrete action space. And then precision recall F1 or standard, but we went with both the micro and macro versions because macro helps kind of alleviate the issues with respect to overrepresented classes. And then invalid percentage is basically saying, okay, can these models even predict outputs in the right format? How badly do they struggle? And yeah, these are the models that we evaluated for V0.2. All state-of-the-art. Phi0 is a generalist robotics policy by a company called Physical Intelligence. Phi0 with FAST is a new kind of tokenizer that they add to their base model. OpenVLA, same as the model we evaluated in V0.1, and then obviously GPT-4 and 4.1 state-of-the-art VLMs. So basically, we found that they perform really, really badly. So VLMs are not able to adapt to this whole like new domain of like action data, and VLAs also struggle a lot when it goes from real-world robotics to gameplay data. So there's not a lot of transfer even within the action domain. So the maximum possible prior error is 2, and you'll see that most of these models that errors kind of like almost reach that limit. So they struggle a lot. Even the invalid percentages, you'll see that some of them are around 80%. So architecturally and the way they've been trained and their output processing methods don't really allow them to even, generalize to like domains such as like this one. And recall is very bad as well. So overall performance really bad. Very hard to generalize given the current state of architectural design, input processing, output processing, training methods. Very insightful, especially when with our goal for Multinet to build these like generalist like benchmarks that assess how good foundation models are across all these different modalities and tasks. So one interesting result in V0.2 that I want to just highlight. This is all you can read more about in our paper, our website. It's all on the website. This one is interesting because it kind of like showed us how the architecture of these models influence the results. So what this is basically the frequency of these models predicting a certain action class within the discrete action space, right? So the action space is 0 to 12, and how often do they predict a certain class when the ground truth is a certain class? And one thing we saw is that the autoregressive models, which are the GPT-4o, 4.1, OpenVLA, and the Phi0 with the fast tokenizer. First of all, there's a phenomenon where when they are evaluated in data that is unseen, and if it's a discrete action space, the predictions kind of collapse to 1 or maybe 1 to 3 action classes. And they're not necessarily the right action class. It's most often the wrong one. But they collapse and concentrate, and you can see like kind of like the darker vertical lines that show the concentration of their predictions. And one interesting thing is that with autoregressive models, you'll see that this action class collapse is highly concentrated. But for Pi0 base, which is a diffusion-based model, you'll see that the predictions are kind of like distributed. And this kind of goes back to, again, like how they're built. Autoregressive models are forced to predict a specific action class because they're softmax at the end during their inference. But with diffusion models, they're basically trying to model how their training data looks. And they're trying to say, hey, like, this is what we were trained on, and this is new unseen data. How close can we get it to what we've seen in the training data? So their predictions are very distributed, diffused, and you can see it very clearly in this confusion matrix. So this is a very interesting result and informs us about how we want to build these models as we go forward. Yeah, so a lot of exciting things coming up with Multinet. So right now, we're kind of revamping our data set coverage for Multinet because the AI space moves rapidly. There's a lot of new exciting data sets. We want to have very challenging evaluation specific data sets and not focus too much on the pre-training data. And we want to have like very well designed software toolkits for submissions and evaluation harnesses so that the community can engage easily, more people can use it, more people can evaluate their models. And obviously want to continue like profiling these state-of-the-art VLMs, VLAs, generalist models, zero shot on our data sets. And we do want to engage more with the community, especially the model providers, and have them actively collaborate with us and like, evaluate their models when they release their models on Multinet. And longer term, so far we've done offline trajectories and zero shot. We do want to get into few shot evaluations, fine-tuned evaluations, and also like we want to eventually get to like online environments where these models are kind of evaluated in a live setting and get feedback for every action they take. And also we want to make it a live benchmark similar to live bench where we're continually updating it, ensuring that it is a contamination-free benchmark. And just to make sure that none of the new models have been trained on the data that we're evaluating them on. And yeah, so a lot of exciting stuff. we're scaling up the team, we're scaling up the efforts. If you're interested, next slide, please. I think, yeah, it shows everyone how you can reach out to us. Feel free to drop any feedback, thoughts, reach out to us if you want to contribute, collaborate. All of us, me, Deb, Locke, Harsh, and Sean and Ridil. And so, yeah, that's it from Martina. Thanks, guys.
Yep, it's me. Sorry about that, guys. So, yeah, we'll be talking a bit about multimodal action models. So, what Pranav presented was sort of the background around how we expect to evaluate next generation models, but we're also building them. And so this is kind of the research project that's covering that direction. So, one thing to sort of motivate is our perspective on why generalist multimodal models matter. So, obviously, these days, AI agents are the rage, and you're seeing sort of a spectrum of different takes on capabilities. Some are very structured and simple, have simple sort of programmatic sort of imperative setups. Whereas in other ones, you start to see LLMs in the driver's seat doing things like function calling. And now we even have sort of computer use as a very exciting direction, which we actually are also working on, and Locke will be talking about shortly. But the idea of building truly multi-capable agents that can dynamically do tasks across different modalities is still something that we haven't really yet seen. And one of the research perspectives that we as a group have, and some of our collaborators have as well, is that it has to do with the underlying learner. So we're really excited about this concept of building new kinds of foundation models that are trained on a variety of different data distributions that cover everything from different modalities like vision or language, but also grounding those modalities into things like control tasks, and then using that learner to fine tune into different application areas. And there's sort of an emerging history to these kinds of models that you can trace through time, including a history here at Manifold. We've worked on models like this for the past few years. So all the way from a few years ago with the release of Gato from DeepMind, well, there was never actually code release, but the sort of paper release of this model, people started to toy with the idea of unifying or trying to jointly ground across a bunch of different modalities and seeing what that model can do. Over time, you've started to see the emergence of vision language action models. You heard Pranav talk about them in the context of some of the assessments and evaluations we're doing. And recently, you can see OpenVLA, Pi0. These models exhibit interesting improvements in downstream action performance on robotics tasks, often for specific sort of embodiments, but sometimes many sets of embodiments, by leveraging some sort of implicit knowledge that's within language and vision. And so they're often using pre-trained backbones of large language models or vision language models to effectively transfer to these action domains. And even more recently, you see more aggressive projects like Magma trying to basically do this at a larger scale. And so we're really excited about and are actively building. Historically, we built Neko, which was the first sort of open implementation of a Gato style model. And we are building new kinds of foundational, what we think of as omnimodal action models. And so we really think about these in the early days as models that are trained on, yes, these large sort of multimodal pre-training distributions, but they're really trained to go from any modality to any modality, and specifically to be able to spit out actions, right? So we think of these as almost from the sort of RL formulation or robotics formulation, forcing these models to act on world scenes. And in doing so, building a new kind of foundational learner that can fine tune into a lot of really, really useful action grounded applications and hopefully realize the dream of autonomous AI agents, or at least make a big step in that direction. So this is very early for us. Right now, we haven't launched any public models yet, but we're totally recruiting to work on this in the open source and try to make as much progress here as possible. So if you're interested in working on this, please reach out. And this work isn't really limited to looking at models in isolation. Obviously, it touches state-of-the-art evals like Pranav was discussing, and also trying to leverage these for some of the tool use applications we're thinking about, which is the perfect transition to Locke's presentation, which is coming next. I wanted to point out that this work and Multinet and also the software control work that Locke is about to present are in collaboration with MedArc AI as well as the Multisensory Intelligence Group at MIT. So if you'd also like to collaborate from an organizational standpoint, please reach out. And you can reach out to Pranav or I in particular about this project to just understand more or ask any questions. So that's it for me. I think now we can transition to Locke's presentation.
Hi, everybody. I'm Locke. So software control models is a new program that we're starting. And what are software control model? So since 2024, we've been seeing a transition from multi-agent systems to native agent models, which we usually build on a multimodal vision language model base and trained with procedural workflow data and GUI visual question answering, reasoning data, computer use data, for example. So the models like UiTAR's GTA-1 with O3 and OpenAI's computer use agents, they all follow this type of structure, and they were trained to take observations like screenshots and text instructions and sometimes HTML or DOM tree to represent the states, and then it spits out sometimes plans or reasoning in the form of chain of thoughts and or code or actions that are compatible with many software interfaces, such as on applicational and also OS level. So usually you see actions such as mouse clicks, drag actions, text input, etc. And so where are we at today? Why are software control models important? First of all, software is everywhere, and software interfaces are diverse and multimodal. It's more than just what the current coding models support in text interface. And there are many like software environments such as robotic simulation like Gazebo, AirSim, or even design softwares like AutoCAD that would involve both vision and text modalities. And multi-agent systems are very brittle and limited by the underlying learners, as Hirsch mentioned. And of course, everybody wants to build a helpful assistance to automate many software tasks like Java's. Next slide, please. So where we at today with software control models, there have been many different types of benchmarks, and they can be categorized roughly into offline static benchmark and online simulation-based benchmarks. And then by platforms, you have desktop, mobile, and web benchmarks. And by the targeting capabilities, you have visual grounding or action-based multi-step planning benchmarks. And the two most famous ones are on the left, you can see ScreenSpot Pro, which focuses more on visual GUI grounding tasks. And on the right, you can see OS World, which spins up virtual machine instance to simulate an environment for agents to perform digital tasks. And with today's SOTA, the leading model can only perform 45 can only score 45.2 on OS World, and they can only achieve 61.6 on ScreenSpot Pro. And even then, most of these performances are not very consistent and robust. Next slide, please. So we have seen current challenges for like generalization on unseen components, or visual grounding that has troubles understanding GUI component affordance, especially unseen ones, and also reasoning the visual layout. And in terms of planning, these models have trouble recovering from error states or tracking the overall task progression. And as for what's for us, our software control model program is planning to work on 3 fronts: eval data and model. And specifically, we're going to build systematic and rigorous evaluation frameworks that supports the downstream data curation augmentation pipeline, and therefore to support us to build better and more robust and functional models. And yeah, that's it for software control models.
Excellent. Thank you guys so much. Thanks, Golem team. So you guys heard from our Golem program. There's a lot of amazing work being done there on generalist sort of intelligence. We have one other major program that we're working on, which is a little bit different than the sort of generalist intelligence work, because we're looking at a sort of constrained area, which is space robotic swarms. And these sort of swarms, space robotics in particular, are computationally constrained. And also we're looking at swarm systems, decentralized systems, which mean that we have to look at the other families of bio-inspired sort of computation. Things like embodied evolution or online adaptation, the way that swarms kind of work in nature. We have to look at these sorts of things for this program, for this unique sort of challenging scenario. And so I'll go ahead and get into a few of our projects. We have two main projects that we're working on. One of them has sort of two sub-projects within it. And the first one that we are working on is the Modular Space Systems Assembly project. So this project is basically focused on, exactly as it sounds in the name, putting together sort of modular reconfigurable space systems, which are the frontier of spacecraft and space structure design. More and more sort of projects are being done to create these sorts of modular systems. There are several advantages to this. Launches are expensive. Launching a single-use object is very expensive and a single use, so you have to keep launching things. What if instead we could reconfigure the structure online or add to it as time goes on, rather than completely decommissioning that spacecraft and launching another one to replace it? So there are certain advantages to using a sort of modular reconfigurable design, and we see this design cropping up all the time. But there are some challenges associated with the assembly of modular space structures. Before we get into those challenges, let's briefly talk about what are the two sort of main paradigms that you could have a structure assemble itself in space, because your options are kind of limited. You mainly have two assembly paradigms. One of them is free flying. So if all the modules can fly, then they can sort of dock and assemble themselves that way. And if they're not capable of free flying, then the other most common sort of paradigm that we see is this magnetic pivoting mechanism. So we have a sub-project focused on each of these two paradigms for self-assembly. And our goal with this project is to create an algorithm that can plan the trajectories and control for each of these modules such that any arbitrary configuration can be created. That's our goal for this project. Okay, so the first modality that we talked about was the sort of flying cube modality. This is where the cubes can fly. And the objective here is to assemble into any desired shape. The sort of unique parts of this project are the safety constraints. If the cubes are capable of flying, then they're capable of smashing into each other at a high speed. And so that's sort of the main considerations that we are looking at with this problem. So this project is like a highly constrained optimization problem. I have a couple of demo videos here of some work that we're doing right now. So in this first sort of video, these are very rudimentary and they're not perfect at all yet, but just to give a sort of idea of what we're trying to do. In this first video, our cubes are assembling they're flying together into a P for Purdue, because that's where I'm doing my PhD and where our project team is. And then in the second one, they're turning into a 2x2x2 cube. So some fairly simple sort of shapes, just to give a quick idea of what we're working on. This is, an early demonstration of this project. I'm just going to wait for those guys to come together. Okay, cool. All right, so that's the flying cube sub-project. The second modality, our project lead, Ben, will talk about that, and that is our pivoting cube sub-project. So go ahead and take it away, Ben.
Hey, I'm Ben. And so I'm speaking on the pivoting cube sub-project. Pivoting cubes are uniform modules that use electromagnetic coupling and decoupling to pivot around each other so that they can reconfigure themselves into any kind of shape. There's a few safety constraints on the available pivoting maneuvers, which makes pivoting an interesting localization and pathfinding problem for each module. The interconnectivity of the modules lends itself to swarm communication and movement. And we're currently developing a reinforcement learning approach that can leverage these swarm attributes to allow for the modules to coordinate and move in parallel with each other. So at the right, we visualize the learning process of our current model. And so we're currently developing that. We look forward to showing you more soon.
Excellent, Ben. Thank you. So those are our two sort of main active modular space systems assembly sub-projects. Work is actively ongoing there. The second project that is part of the Ethermorph direction right now is this sort of crowded orbit navigation project. So in the modular space systems assembly project, we talked about sort of this constrained situation where modules need to navigate their relative geometry to assemble properly because there are wrong ways to assemble. This crowded orbit navigation is a different kind of problem. So just to briefly touch on the motivation for this second project, low Earth orbit is very crowded. We've talked about this, I've spoken about this in previous CRCs, but there's this thing called Kessler syndrome where at some point the amount of debris in space is going to start making more debris. And we need methods to navigate this sort of minefield, or I guess like this bullet hell environment that satellites find themselves in orbit. In the first half of 2024, Starlink satellites executed 50,000 collision avoidance maneuvers, and the way that they calculate these collision avoidance maneuvers is very rudimentary. They basically receive a ping from the U.S. government saying collision is imminent, and you need to move in one of the 6 sort of cardinal directions and avoid it. There's a need for scalable, optimal navigation solutions that conserve fuel and work for distributions of spacecraft rather than just single spacecraft. And that's kind of what we're targeting here. So on the right is sort of a brief demo of what we've got so far. Our approach is to use operator learning, neural operators. We're using a multi-headed transformer to sort of approximate this neural operator. And the purpose of the neural operator is to generate a set of trajectories for one distribution to go to another target distribution. This sort of distribution to distribution mapping is sort of unique and ongoing area of research in areas like optimal transport and flow matching problems. But it's kind of suited for this circumstance where you need a distribution of satellites to navigate through a distribution of obstacles and wind up in the correct sort of terminal distribution, right? It is uniquely suited to swarms. So this is sort of another thing that we're exploring is this distribution to distribution trajectory optimization in the context of navigating crowded orbits. So this is the second project in the Ethermorph direction. Okay, great. So now we will touch on some of our upcoming projects. And Harsh, I believe that you're going to talk about the first one.
Yep, I can go ahead and take over. So slide please. So yes, first we have a new emerging program. So if you recall, I think by now maybe you have an idea of the difference between programs and projects. So projects are more about individual research projects, who would have thought? And programs are the larger overarching missions that those projects add up to, which often have some sort of large scale technical goal. So we're launching a new program and it's called Supercluster. And the focus here is to solve some of the fundamental challenges in distributed and decentralized AI training and inference. And so, you know, obviously the world is going crazy with the amount of AI that's being built, literally the amount of models being trained, the scale of those models. But one ongoing challenge that has been perpetually around for the past several years as model training has become a big deal and the scale of these models has become large is how do you effectively do that across a bunch of heterogeneous compute units? For us, that's really, really interesting because we have so many frontier directions that, you know, we're not on a sort of urgent time scale that we need to get models trained within necessarily a week or something like that, but rather we want to work with lots and lots of different clusters at some of our academic and industry partners to be able to work on the next generation technologies that we are trying to build and the AI system specifically. And so oftentimes, in this case, decentralized and or large scale distributed, you know, non-localized training becomes really, really useful. And these are two different, you know, on a spectrum, there's sort of a nearer term goal and a longer term goal. And so we are directly starting a program to work with some of our partners and anyone else who wants to collaborate with us on building new kinds of algorithms to facilitate this kind of sort of data transfer, training processes and inference processes at massive scale. One way to think about this is if you had to build a sort of Stargate style cluster, but you could only do it with distributed technologies, how would you do it? Right. And that's kind of the operative theme here. And we want to be able to leverage this with everybody to be able to do a lot of communal training of large-scale AI systems. And so we'll need to work at pretty much every level of this abstraction. And we are basically building the first sort of core team to go for this, finding the right PI. So if you're interested, please reach out in participating or even leading this. And or if you have references to great scientists that you think would be awesome to have, please do reach out. You can reach out to me at hersick@georgiatech.edu or on Discord as well. Slide. Another thing I want to discuss, this is less of a program, but a new sort of independent initiative that we're pursuing. So we talked a lot about next generation intelligence, especially in the context of the Golem program. We've also talked a lot about evaluations. You heard about the VLM calibration project. You heard about the multi-net project, which is a large-scale evaluation. You can imagine that, for example, for software control systems, you also need to build really powerful evaluations. Generally, the world is echoing back this insight, and we see that new generations of AI systems are becoming increasingly powerful and are being expected to act in increasingly agentic ways. And we want to build the evaluation systems, not just the specific evaluations, but the way that eval should be handled to support this next generation of systems where current benchmarks have become saturated and fail, often because of their static nature. So we're launching a new independent initiative called FASE, which stands for Frontier AI Systems Evaluation, which focuses on facilitating and supporting living benchmarks. So that's both the benchmarks that we're developing, things like multi-net, and other benchmarks that we're releasing soon, but also any community submitted benchmarks as well. So we want to work with as many folks to keep benchmarks live and updated as possible so that we can continue to evaluate systems live. And we have a big sort of vision for where this goes beyond just building static benchmarks, but all the way through to building really powerful world model simulators for the new complex kinds of AI that are going to get built. So if you're interested in this in any capacity, please reach out. We are actively building this initiative. We expect to launch public presence for this in the next couple of weeks. So really excited about this. I'll briefly present on behalf of Helen Liu. So Helen Liu is a core team member, a great researcher that we have on the team here, and she's also a PhD student at Tufts. And she is starting a new project at Manifold in collaboration with her team at Tufts and several other postdocs, PhD students, and faculty members to start to understand and build interpretability approaches for vision language action models. So obviously, you know about the promise that VLAs show, so I don't need to go over the significance of VLAs and how this multimodal action future is a very powerful trend that we want to understand more about and build for. But probing, a common problem that emerges in these VLAs is that they often fail in really spectacular ways, and it's not clear exactly how efficiently they are leveraging their sort of pre-trained backbone and why certain transfer fails. So we're launching an experiment and a whole sort of a project direction, which falls into the Golem program, to specifically explore the semantics of the learned representation within a VLA. So we want to look in and use sort of simple probing techniques to understand at which layers are semantic representations learned in these vision language action models. So put more simply, where does a vision language action model that's supposed to pick up a cup learn about what a cup is? And where does it learn about what pickup means? And if we can isolate and find how these things are represented, we can often find why those failure modes are happening when we see it fail in a bunch of transfer, and then further inform from a learning perspective how we should better build this next generation of models to effectively transfer, which again ties back to a lot of the multimodal action model direction that we were discussing earlier and why we're excited about that. So this is a new project. We're actively recruiting for this. Please reach out to Helen, who's the project lead. And yeah, really excited about this. I think this is back to you, so.
Yep, back to me. So thanks, Harsh, for presenting on the VLA probing. Another upcoming project that we have after the modular space systems assembly project, actually I should say after the Flying Cube modular space systems assembly project, is to take it one step farther and have a swarm of assembly agents put together a structure instead of having the structure assemble itself. So this is sort of the next natural step in this direction. And this is going towards the holy grail outcome of having a swarm of agents in space put together arbitrary structures, put together spaceships, put together space stations, whatever, mining stations, factories, whatever you want. This is what we need to do first. There are some complexities that are associated with this having a swarm of assembly agents put together a structure. Those complexities are the things that we plan to address in this project. So those are things like the assemblers may be free flying or they may be attached to something that they're moving. That changes the dynamics of the assembly agent. multiple assemblers may be moving the same module, so then they have to coordinate, and their dynamics become strongly coupled. The thrust from one directly affects the state of the other. And then there are these sort of non-holonomic constraints, which means that you can't move along all three sort of axes necessarily. There may be restrictions to what directions that you can apply your thrust in. So there are some complexities associated, and this is kind of where we want to go next with this project. So with this direction. So this project is coming up soon, so keep an eye out for that. And then that was the follow-up to the Flying Cube Modular Space Systems Assembly project, the follow-up to the Pivoting Cube Modular Space Systems Assembly project, which is what Ben is leading, is to have these pivoting cube systems basically start to adapt on their own in open-ended ways. The first way that they could do this is through sort of self-healing, right? Like if an external module gets damaged, then pivoting and reconfiguring so that the external module goes to the interior and some interior fresh module goes to the exterior. That would be an example of like shape-shifting for the purpose of self-healing or replacing damaged modules. And then another example is like altering the geometry of the system so that they can generate better energy through increasing their area affected by the sunlight, or maybe becoming more aerodynamic so they can move through an atmosphere better. It's sort of an open-ended adaptation thing that we're looking at. It's challenging for multiple reasons. You know, it's decentralized, and like I said, it's open-ended adaptation. And these modules are compute restricted. Like I had mentioned before, in space, everything is compute restricted because the hardware has to be radiation resistant. And so we're looking into sort of bio-inspired methods. You know, there are things in nature that do this sort of reconfiguration. Cells, for example, do this morphogenetic reconfiguration. They turn into organs. They heal from damage. So looking into some of those algorithms that nature uses, that's kind of where we're going with this project. So this is going to be the follow-up to the Pivoting Cube Modular Space Systems project. Okay, so briefly wanted to touch on those. So those are our upcoming projects and programs. What else is next at Manifold? So multiple teams have said, but projects are recruiting. We're scaling on all the efforts that we talked about today. And also our OS operations team is recruiting as well. So be sure to check out the opportunities page on our website to see postings as they go up, and to join us, to join the mission. One brief thing that I want to say about the OS operations team, during these community research calls, we mostly talk about the research, of course, that's in the name, but our operations efforts are also expanding. We are trying to build out better and better ways for this research to basically interface with the real world. It's easy for research to exist in an ivory tower. We don't want that to be the case. The research is only good when it actually affects the real world. And that's our goal here at Manifold, is to maximize the impact of our work. Okay, so in the interest of sort of maximizing the impact of our work and maximizing our reach, we also want to support and foster as many projects as we can. So we've recently launched this community project system, which is live right now in the Discord. And we already have a couple of posts there. The purpose of this community project system is for you guys, anybody who has a breakthrough project idea, to make a post and we can discuss it. And you can find collaborators. We can assist with drafting. There are many sort of bottlenecks to research that, you know, people may feel uncomfortable or unprepared to go through, but you don't have to go through it alone. We can go through it together. You know, the Manifold community has a lot of great research talent within it, and let's work together. Let's make some breakthrough things happen. Awesome, guys. So thank you so much for attending the community research call today. I'm just going to briefly. Okay. So more information on everything is available on our website. It's constantly being updated with new content. If you check, our research page is completely overhauled from maybe the last time you've seen it. It reflects sort of our active research directions right now. I strongly encourage everybody to check that out. You can email us directly at team@manifoldrg.com. We put recordings of this event and others on our YouTube channel. We also host these events and post about them using our Luma calendar. So you can check that, subscribe to that for any future events. And then, of course, we have our Discord community, our GitHubs, our GitHub repos, and then we have an active LinkedIn and Twitter that we post from regularly with updates across the board. So thank you, guys. Harsh, any final comments?
No, thank you all for attending. This is awesome, and we look forward to sharing some big updates in the next couple months as well. Thanks, everyone.
Thanks, everyone. Have a great day.
Take care.